Hi everyone, welcome to our new unit. And so this unit, as I mentioned before, is called dynamics, right? Our last unit was called kinematics, and it was the study of how things move. And so now what we're going to do is we're going to study why things move. And it's long been understood that objects move because of forces that are acting on them. And the definition of a force is basically a push or a pull. So exactly what you would think about. Okay, so that's a force. And what we're going to learn in this unit is we're going to really learn what a force does in terms of how the object moves. Does an object have to have a force in order to keep moving? All right, so these are a lot of questions that physicists from way back when asked. All right, and so this is what we're going to be studying. So the first thing we have to do is kind of look at what kind of forces there are, and then from there we'll go on. Now, scientists believe that there are 4 fundamental forces in nature. So all the different types of forces that we can imagine can be narrowed down to 4 different basic fundamental forces. I'm sure you've heard of 2 of them. So I want you to think. Can you think of any of these 4 forces? So what's the first force that you can think of? My guess is you would say gravitational force. And you would be right. So the force of gravity is one of the 4 fundamental forces. And this is a force that large masses, exert on objects. Okay, and we'll get into more detail about this. Is sort of a basic definition. We'll get into it a little bit more later because that's not really the definition. But when you think of masses like the Earth, the Sun, Saturn, those are large masses and they exert forces on objects. Okay, and we'll get into it a little bit more later. But that's one of the fundamental forces of nature. There's 3 others. So what are the 3 others? So aside from the force of gravity, these are the 3 other fundamental forces, and they're not as well known. The electromagnetic force you may have heard of. This is the force of how magnets work. Okay, and we'll talk more about it in Unit 4, and also how electric charges work. So if you think about in grade 9 science, when you did static electricity, that'd be electromagnetic force. But more importantly, the electromagnetic force, that's the force that holds, all molecules together. It's also known as the intermolecular force. And so if you learn chemistry, if you do chemistry, you're going to learn more about these forces. But for example, when you talk about water and why does water cling to each other? Or why does a molecule like ionic bonding, which you learned in grade 10. So if you remember in grade 10, when you had sodium chloride, sodium is a positive ion and chlorine is a negative ion. And why do they stay together? Well, that's the electromagnetic force that holds them together. And that's why salt stays as salt, right? So these are the forces that sort of hold molecules together. Now, if you were to decide, is gravity stronger or is the electromagnetic force stronger? What do you suppose is stronger and what do you say is weaker? So a lot of people would think gravity is stronger, but in fact, the electromagnetic force is stronger. In fact, the electromagnetic force is about 10 to the 28 times stronger than gravity. What does that mean, 10 to the 28? So imagine a 1 with 28 zeros after it. I'm not going to write all the zeros, but imagine that's how many times stronger electromagnetic force is. And actually, that's a very good thing for us. Because imagine if gravity was stronger, then the chair that you're sitting in would not hold up. Because gravity would be so strong, it would pull you through the molecules of the chair that you're sitting in. In fact, your house wouldn't be able to stay up because it would gravity would pull you through the molecules of your house. Thankfully for us, electromagnetic force is extremely strong and gravity is extremely weak. And I know you don't think of gravity as weak, but just jump and you've already overcome gravity. So gravity is actually an extremely weak force. All right, now the other two forces you've probably never heard of. And if you did, that's unbelievable because very few people have, right? Because these forces, they work at a long distance. And so by long distance, I mean big enough for us to see. As you can see for these bottom two forces, where it says nuclear, they only work at a distance of a nucleus of an atom. So it's unbelievably short distances. And so these two forces weren't even discovered until about 100 years ago, right? Gravity, people have known existed forever. Even magnetism, they've known existed forever. So as long as man has been around, they've known about sort of like these two forces. But these ones, they were discovered very recently when we started to study the atom. So what are these two forces? So the weak nuclear force, that's the force that holds, protons and neutrons together. And it's responsible for radioactivity. The strong nuclear force is the force that holds an atomic nucleus together. Okay? And it's the strongest force there is. So this force itself is about 1,000,000 times stronger than electromagnetic force, and I don't know how many million times stronger than the weak nuclear force, and then gravity is the weakest force of all. So if we want to look at the order of strength, it goes strong nuclear force, then the electromagnetic force, then the weak nuclear force, and finally gravity, which is by far the weakest. All right, so that's the order of strength, and these are the four fundamental forces of nature. Now, to be honest, except for gravity, which we will also look at, all the forces we experience in everyday life is an electromagnetic force. So if you think about somebody pushing you, you hitting something, right? All of these forces that you talk about, they're all electromagnetic forces. So in this course, we will look at gravity and all of these other forces. And that's it. We will not look at the weak or strong nuclear force. We'll talk about those in grade 12. Now these electromagnetic forces, what are some of the common forces, right, that we see, right? So obviously the force of gravity, which we know, and the symbol for the force of gravity is Fg, okay? Force is a vector, so they all are going to have their arrows. The normal force we'll talk a little bit about, but this is the force that acts perpendicular to a surface. So it's really the force that's keeping you up right now when you're sitting on your chair. It's your chair pushing up on you, holding you up, right? And very often that normal force balances out the force of gravity. All right, so we will talk more about the normal force as the lesson continues. Another force is the force of friction, right? So this is the force that opposes motion. There's an applied force, so that's the force that someone would push or pull on an object, okay? Force applied to an object. And finally, there's a tension force, which is the force exerted by a rope or string. So you can see that the symbol for force is F, and then we use a little subscript here depending on which force we're looking at. Force of friction, normal force of gravity, applied force, force of tension. Okay? The unit for the force is named after Sir Isaac Newton, and therefore it's called a Newton. So the unit of force is a Newton, and we use the letter N right here, a capital N, to represent it. The feel of a Newton, if you want to think about it, is about 220 grams, or about a small apple. So if you pick up an apple and sort of feel the heft of it, that's about a Newton. And it's a small apple, not those gigantic, like, Honeycrisp apples or anything like that. A smaller apple. All right, and when we're in class, we'll take a look at it. Since the force can be applied in a particular direction, as I said, force is a vector quantity. Now, in order to study forces, it's much easier if we draw a very simplified diagram. And that simplified diagram is called a free body diagram, or FBD. Okay, free body diagram. And it's basically a diagram of all the forces acting on an object. So whenever we do a forces question, any single time you do a forces question, you're going to have to draw a free body diagram for it. And you have to stop and think, okay, what would all the forces sort of acting on this object, what would they be? So here's a bunch of examples. So let's take a look. So the first one is a book resting on a desk. Okay, so first of all, it would be a pain if I have to draw sort of the book, right? There's my book. I have to draw my book each time and then have a desk. Oh my God, if I had to do this every single time, it would take forever. So instead of doing this, what we do is we say, here's the book. It's a box. So all of our objects are a box. And in fact, once you get to university, they don't even bother drawing a box. They'll just draw a dot. And they'll say all the objects are a dot. But let's draw a box because it's easier to look at our forces. The desk I will draw as a flat surface. So what are the forces that are acting on this book? So the book is not moving. It's just resting on the desk. So the first force is for sure gravity. Because gravity is, if we're on Earth, there's always going to be gravity. So the only time you don't have to draw gravity is if we're out in space somewhere. Okay, so put in gravity. So gravity always acts downwards. So that's going to be gravity there, and it's going to be an arrow pointing down. Now, if there was nothing else there, if that was the only force, then this book should be falling down. But it's not. So there has to be another force acting on the book, and that force is the force of the desk pushing up on the book. And that's the normal force, okay? So this normal force is the force of the surface, which is the desk, pushing up on the book. And that, see, if you notice now, right, if you notice these two forces are now balanced, and the book is just sitting there because the forces are balanced. And we'll talk more about that in a minute. Now, what happens if the book is pushed across the desk? So now, here's our book. There's still gravity because it's on Earth, and there's still the normal force because the desk is still holding the book up, but now there's an applied force causing the book to go across, and because it's sliding, there's probably friction. If you notice, I've made the applied force much bigger here. This is much bigger than the force of friction, and therefore the object's going to accelerate in this direction. Okay, so it's going to move. How about a stone falling in a vacuum? So let's take a look at what happens there. So if I have a stone that's falling, right, gravity's going to be pulling down on it. If it's a vacuum, that's it. There's nothing else acting on it. And so that's the only this is the only force acting on it, and therefore it's going to accelerate downwards, which we know when you drop an object. If it's falling through air, then there's going to be the force of gravity, and there's going to be some air resistance. So force of the air, which is a type of friction, but not really. Okay, so we're going to look at different types of friction. right? But really it's just the force of the air pushing up. So a stone falling through air would look like this, and a stone falling in a vacuum would look like that. These are all free body diagrams. So it's a simplified diagram of what's happening. Now, if we have to decide whether an object moves or not, okay, so is there motion for an object, you have to look at what's called the net force. Okay, so the net force acting on the object. And that's really just all the forces added together. Or another way of looking at it is the overall force. Okay, so if we know what the overall force on an object is, then we can figure out if, the object's going to move, if it's accelerate, what's it going to do. All right? So we use the symbol F net, okay, to represent net force. So that's our symbol. And if the forces are balanced, then the net force on an object is 0. So let's imagine here's an object, and there's a force of 10 newtons acting this way, 10 newtons acting this way, 3 newtons acting this way, and 3 newtons acting this way. So that's the forces acting on the object. So if you look, this force and this force cancel each other out. And this force cancel each other out. And so at the end, there's a net force of 0 because all the forces balance. So F net is equal to 0. Right? And so this object would not accelerate anywhere. Okay? It would, if it's still, it would remain still. Now, if the forces are exactly opposite to each other, then you can simply subtract them to find the net force. So for example, let's say I have this as 5 newtons, and this is 10 newtons, and I say, well, what's the net force acting on this object? And let's call this side the positive direction and this the negative direction. Okay, it doesn't really matter, but that's what I've decided. So it's going to be 5 newtons plus negative 10 newtons, right? Because if you remember, the net force is the sum of all the forces. So we add all the forces together. And so that's going to be minus 5 newtons, which, if we figure that out, is, 5 newtons to the left. And that's the net force, which makes sense. If you look at this picture, if someone's pushing on this with 5 newtons and someone else is pushing the other way, so someone's pushing this way 5 newtons, the other way 10 newtons, then the overall force is 5 newtons this way. And there it gives you the net force. Now, if the forces are acting in 2 dimensions, then we're going to have to use vector addition, right? So imagine I have this, and I have a force of 3 newtons acting this way, and 4 newtons acting this way. Well, we said the net force is equal to 3, let's call it east, plus 4, we'll call it north, but really it's right and up, but that doesn't matter, Then how do we add those? That's vector addition. So let's do our vector addition. If we remember, it's head to tail. So that's 4, that's 3. That's going to be our net force right there. The resultant is our net force, right, with this angle. So doing our calculations using Pythagorean theorem, hopefully you got the net force as 5 newtons and the angle as 53.1 degrees. And so therefore the net force is equal to 5 newtons. Let's see, the angle is coming off the east, so it'd be east 50 degrees north. And why 50? Because we only should have one significant digit. And so that's how you find net force. So you should be able to do some problems based on that. So let's try a simple question here. Calculate the net force acting on an object. If here's your object, you have 67 newtons going east. Oops, not north, east, newtons. And 32 newtons going south. Now this should be bigger because it's 60, it's almost double. Okay, so this is what we have here. So again, we use our vector addition. There's your net force. This is 67. This is 32. So what would you get? So hopefully you're able to calculate and get this answer here. So you would get F net equals 74 newtons east, 26 degrees south. Okay, so hopefully you got that as your answer once you tried calculating it on your own. Okay, so hopefully you guys understand what force is and what we mean by net force and what a free body diagram is. We'll stop here, and I'll see you guys at our next video.